All right, today we're diving into one of the biggest, most mind-bending questions we can possibly ask. And we're going to look at it through the lens of a really powerful and, yeah, pretty controversial idea, the rare Earth hypothesis. So let's just jump right in. Think about it. Our universe is stuffed with an absolutely staggering number of stars and planets. I mean, the numbers are almost meaningless, they're so big. So you'd think it would be buzzing with life, right? And that at least some of that life would be intelligent. But when we actually look up and listen, there's just silence, a deep cosmic quiet. And that's the famous Fermi Paradox in a nutshell. Where is everybody? You know, for hundreds of years, the basic assumption has been that we're not special. That's the Copernican principle, the idea that Earth is just your average rocky planet orbiting a totally normal star, so life should be everywhere. But that silence, it hints at something else, a much more challenging idea called the rare Earth hypothesis. And it says the exact opposite, that complex life like us, is an almost impossible accident. Now here's the key distinction, and it's super important. The hypothesis, which comes from scientists Peter Ward and Donald Brownlee, doesn't say all life is rare. In fact, it suggests that simple stuff, microbial life, slime, that could be all over the place. But the leap from a single cell to, say, an animal or a plant, well, that's not a given. It's not an easy, straight path. Instead, it means you have to win a whole series of cosmic lotteries, one after another, in a sequence so unlikely it might have only happened once. Right here. So where does this incredibly long shot of a journey even begin? Well, not on a planet, not even in a solar system. We have to zoom way, way out, to the scale of the entire galaxy. Because the first great hurdle is just being in the right cosmic neighborhood. So let's talk about something called the Galactic Habitable Zone. You've probably heard of the habitable zone around a star, right? The Goldilocks zone where water can be liquid. Well, this is the exact same idea, just scaled up to galactic proportions. It's a very specific, pretty narrow ring inside the galaxy where conditions are, well, just right for life to even have a shot. And what this creates is this incredible cosmic tightrope walk. See, to even build a rocky planet like Earth, you need heavy elements, what astronomers just call metals, and those are cooked up inside stars. So you need to be in a part of the galaxy where lots of stars have already lived and died. But if you get too close to the galactic center where all the action is, you're getting blasted with lethal radiation and constantly threatened by nearby supernova that would just sterilize everything. So you're stuck in this narrow, just right band of safety and resources. Okay, so let's say you found the perfect piece of galactic real estate. Now for the next filter, your landlord, the star itself. The thing is, the evolution of complex life takes billions of years of calm and stability. That means you need a star that's not too hot, not too cold, and doesn't throw temper tantrums. You need a star that just chugs along, providing a steady, reliable stream of energy for eons. And that sweet spot seems to be for stars a lot like our sun, in a pretty narrow category called F7 to K1. And this filter is a monster. I mean, just look at this. The most common type of star out there, making up more than 80% of all stars, are these little M-dwarfs. But they are just terrible for life. They shoot off these violent flares that would fry any nearby planet. And to be warm enough for liquid water, a planet has to huddle so close that it gets tidally locked. One side forever baked, the other side frozen solid. So boom, just like that, the vast majority of star systems in the galaxy are probably off the table. Okay, so we've passed the galactic filter. We've passed the stellar filter. Let's zoom into the planet itself. And this is where the list of requirements gets, honestly, just breathtakingly specific. We're not just looking for a decent planet anymore. We need an impossibly perfect one. First up, you need a giant moon. Our moon is ridiculously big compared to the size of our planet, and it's probably the result of a crazy, freak collision billions of years ago. So why is that so important? Because our moon acts like a gravitational anchor, like a giant gyroscope for the whole planet. It keeps Earth's tilt stable so it doesn't just wobble all over the place. Without it, our climate would swing wildly between scorching heat and planet-wide ice ages. Nothing complex could ever evolve. Next, you need the right kind of big brother in your solar system, a Goldilocks gas giant. For a long time, we thought of Jupiter as just our cosmic bodyguard, swatting away dangerous asteroids. But the truth is, it's more complicated. It can also fling them right at us. So you need a Jupiter that's the right size and in exactly the right orbit to act more like a bouncer than a bully. It might have even been the thing that helped deliver water to early Earth in the first place.
And finally, the planet has to be alive on the inside. It needs a churning, active engine, plate tectonics. This is so much more than just continents drifting around. This is Earth's long-term climate thermostat. Through volcanoes and the slow weathering of rocks, this whole cycle regulates the amount of carbon dioxide in our atmosphere. It's the very thing that has kept our planet from turning into a frozen snowball or a runaway greenhouse like Venus. It's what's kept the water liquid for billions of years.
Let's just pause here for a second and let that sink in. A giant moon for a stable climate, a perfectly placed gas giant for protection, and active plate tectonics to keep the temperature just right over the long haul. The rare Earth hypothesis says you need all three, and each one of these things is a pretty unlikely event on its own. The odds of all of them happening to the same world, they're just astronomically low, and maybe, just maybe, that's another piece of the puzzle explaining that great cosmic silence. Okay, but let's just imagine. Let's imagine a planet actually wins this incredible cosmic and planetary lottery. Even then, the journey is far from over. In fact, some of the hardest challenges are still ahead. Now we have to look at the massive biological hurdles life has to clear. This next step, this might just be the single biggest filter in the history of life, anywhere. For billions of years, life on Earth was just simple bacteria, prokaryotes, and they're stuck, limited by a basic energy problem. Then, maybe only once in 4 billion years, something completely bizarre happened. One simple cell swallowed another one, but instead of eating it, it put it to work. That little guest became the mitochondrion, the power plant inside every single complex cell today. This 1 in a billion merger created our ancient ancestor, the eukaryote, and it unleashed an energy revolution that made all complex life possible. And the challenges just kept on coming. After that big leap, life had to survive these insane deep freeze events called snowball Earth, where the whole planet was basically a ball of ice. Then life itself had to totally re-engineer the planet's atmosphere, pumping out enough oxygen to make it breathable for animals like us. That's the Great Oxygenation Event. Each one of these is just another massive, improbable barrier to overcome. So, when you start multiplying the odds of all these filters, the galactic one, the star, the perfect planet, the impossible biology, you're left with a number that's just vanishingly small. You're left with a pretty powerful, if a little terrifying, explanation for the great cosmic silence. Of course, it's really important to say that this is a very controversial idea. The main criticism you'll hear is that it's just too Earth-centric, that it suffers from a lack of imagination. Critics basically say, hey, you're just listing the way life happened here and assuming it's the only way it could happen. And there are some really compelling alternatives, for sure. I mean, could complex life exist in the deep, dark oceans under the ice of a moon like Jupiter's Europa, warmed by gravity instead of a sun? What about the wild ecosystems we've found here on Earth around deep-sea vents that don't rely on sunlight at all? If life can find a way in places like that, well then maybe a lot of those rare Earth rules just don't apply. But if the rare Earth hypothesis is right, even just broadly right, the conclusion is pretty stark. The reason the universe is quiet isn't because something bad is waiting for us in the future. It's because the great filter, that huge barrier to intelligent life, is already behind us. The silence explained because complex, intelligent life is such a fluke that it almost never happens at all. Ultimately, this idea just completely flips our whole perspective. It suggests that Earth isn't just some boring, typical rock in a crowded galaxy, but that it's a nearly impossible jewel box of life and complexity. It suggests that we are the profound exception, not the rule. And it leaves us with one of the most sobering and awe-inspiring questions we could ever ask ourselves. What if we're truly alone?